Hi, good afternoon everybody. I think we can get started because it's 3:15 already. So my name is Anand Ramachandran and along with me I have my colleague Greg. Both of us will be presenting this session here on Scalable Virtual Edge. So here is the agenda for the talk today. So we'll start off by looking at the landscape for hybrid cloud networking, look at why virtual network functions are actually needed, and then we'll take a deep look at all the different virtualized network functions that we are offering in 2012 R2 and in Windows Server V next. So let's start with the landscape. Organizations are rapidly moving all their workloads into the cloud, and they have a specific set of requirements. Given that they are moving so much into the cloud, they look at the cloud as a natural extension of their on-premises network, and what this means is that they want to be able to connect to it very easily, securely, and in a very optimized manner. They are also trying to replicate their on-premises network into the cloud. What this basically means for us is that they have a specific set of network functions that they have deployed for these workloads on premises, and now they want to take all that and provide them in the cloud. And sometimes the reason for this is also compliance. So you have some use cases where it is a federal compliance, like if it's a bank or a financial institution which is storing sensitive data in the cloud, you're required to deploy some security functions there to protect all this data, like data loss prevention or something like that. So that is one of the big use cases why all these organizations need network functions in the cloud. Some of them, what they are doing is they are trying to take their network appliances which are there on premises and moving it to the cloud. The advantage of doing this is that they are able to take appliances that they are very familiar with, which they know how to configure, they know the set of features that these appliances offer. And sometimes it's also to comply with the company policies, where the policy says that you have to use specific vendors, specific appliances, specific configurations, etc. Now let us look at the cloud service provider who has complementary requirements. He basically wants to encourage all these organizations to move more and more stuff into the cloud, and for that he wants to be able to provide flexible and seamless migration of workloads into his cloud. He knows that all these organizations want to protect their workloads, want network functions for their workloads, so he wants to provide a native set of basic network functions for these workloads. And he also wants to provide the flexibility to allow organizations to bring their virtual appliances into the cloud. So once he has deployed these network functions, he wants to be able to easily manage them, both from the point of view of the organization or the tenant which configures them, etc., and also from the deployment point of view for the fabric admin. And in doing all this, he wants to reduce the capex and opex incurred. So what is Microsoft's strategy in addressing this area? So what Microsoft wants to do is that we want to go and build first-party appliances, first-party virtualized network appliances for all the key functions, and then provide a platform that allows you to bring your own virtual appliances into the cloud for all the advanced functions. And we set off on that journey with 2012 R2. So 2012 R2 provides a cost-effective and scalable virtualized cloud gateway for hybrid cloud connectivity. So we predominantly address the connectivity part of the story. And in Windows Server Next, we provide the complete set of edge functions that are required. And all these are centrally managed and controlled through the SDN network controller. So what is the network functions virtualization? It is basically taking all the network functions that you are familiar running on hardware appliances and then building them on VMs. So your virtual appliance is essentially becoming a VM. Your network appliance is becoming a VM. And there are multiple advantages of doing this. One is it's very cheap. It is very cheap to buy and deploy all these network functions. You have the flexibility of deployment and management. It is very easy to test and validate them before you roll them out. And then they are highly distributed, so you can move them anywhere in your data center. Now let us look at the network functions that we first offered in 2012 R2 in detail. So in 2012 R2, we introduced the virtualized edge gateway, which offers a bunch of functions. The first one is a site-to-site gateway. The site-to-site gateway enables on-premises enterprises to connect to their workloads in the cloud. So they essentially set up a site-to-site tunnel between their on-premises gateway and the gateway in the cloud. And this cloud gateway that offers site-to-site is basically multi-tenant. So you can terminate connections from multiple enterprises on a single gateway VM. You don't need to go and deploy separate gateway VMs for that. So it is a very cost-effective solution. And it basically utilizes the multi-tenant networking stack, which gives you a virtual stack for every tenant, and through that it basically isolates the traffic of different tenants. It is able to allow IP address overlap between tenants, etc. The gateway is highly redundant, so we use guest clustering for this and provide 1:1 redundancy. So every active gateway has a hot standby gateway. The hot standby is naturally constantly synchronized with all the IPsec routing and other information from the active. So when the active fails, the standby detects that and comes up. It already has all the configuration, and all that you need to do is re-establish all the site-to-site connections, the routing peerings, etc. We have BGP for dynamic routing to basically exchange route information between your on-premises network and the cloud network, and that too is multi-tenant. And what that means is, on the gateway you can have a separate BGP instance running for every tenant. So it runs in the virtual stack or the compartment that has been allotted for that particular tenant. We added capability for a multi-tenant stack in the same gateway, and through this for a multi-tenant NAT in the same gateway, and through that NAT you can basically provide internet connectivity to all your tenants that basically want to access the internet from their VMs in the virtual networks. And it also allows you to publish services that are present in the virtual network to the internet. So if you have say Blue Virtual Network in this case, which has a web server that you want to publish, you can publish it through a public IP, and you can go and do that for all the tenants in the cloud, and you can pack this function for all tenants on a single gateway VM. We also have remote access VPN, and this is for users who want to connect to their cloud workloads from home. And we support both IQ2 based VPN and SSL based VPN, which is SSTP. And a lot of you must be familiar with the built-in VPN client that we have in Windows. It provides a variety of different authentication protocols, etc. All that is supported on this multi-tenant VPN solution also. Management is primarily through SCVMM and PowerShell. SCVMM is what you use to deploy this gateway, configure the fabric, etc. And you also have PowerShell for basically a command line interface. We are also providing a tenant facing portal through which the tenant can come and self-service. He can go and configure the gateway, subscribe to services, monitor them, etc. And that gateway and that is called Catal. That portal is called Catal. So that kind of sums up the offerings of the virtualized edge gateway in 2012 R2. So let us look at the performance metrics that this gateway provides, and all these numbers that you see here have been measured on a VM with 6 cores. So you can support up to 100 tenants on a single gateway VM. You can set up about 200 tunnels to a single gateway VM. The throughput of every IPsec tunnel is about 300 Mbps, and the aggregate for the whole gateway with 100 tenants and 200 site-to-site tunnels is about 1.5 gigabits per second. Using BGP, you can learn up to 15,000 routes, and if you want to set up SSTP VPN connections, you can go up to like 1,000 connections per gateway. So here I have a quick demo of how the 2012 R2 gateway works. So in this setup, I have two enterprises, Blue and Red, and they both have virtual networks in the cloud. These virtual networks have overlapping IP subnets, and there is a web server in each of those virtual networks, and those web servers also have overlapping IPs. And what we're going to do is, I'm going to sit on Blue and I'm going to try and access that particular IP, and you'll see that a Blue website comes up, and I'll access the same IP from the Red enterprise, and a Red website will come up. So let's take a look at the demo.
Here I have my VM console. There is one.
Can you help me with the speakers here?
Configured is 14.110. Connectivity to the Blue subnet is over an IPsec tunnel, and for routing we have BGP enabled. Now the configuration of the VM network for Red is similar. It has an overlapping subnet with Blue, which is 14.110. Now let's look at the configuration of the cloud gateway. Now on the cloud gateway, you see one connection for Blue and one side-to-side connection for red. The side-to-side connection for blue goes to the on-premises gateway for blue, and the side-to-side connection for red goes to the on-premises gateway for red. Now let's look at the workloads for the red and blue tenants in the cloud. So here I have two VMs, one for blue and one for red, and they each run the web servers for blue and red respectively. If you look at the IP address of blue, you see that it is 14.1.1.10, and if you look at the IP address of the red VM, it is again 14.1.1.10. So they have overlapping IP addresses. Now let's look at the configuration on the on-premises side. Let's start with blue. Now if you look at the blue gateway, you see a side-to-side connection, and that side-to-side connection goes to the cloud gateway at 100.10.10.10. The blue gateway has BGP enabled, and through BGP we see that it has a route to the subnet 14.1.1.0, which is nothing but the subnet of blue's VNet in the cloud. Now let's see what red shows. Now red gateway also has a side-to-side connection going to the cloud gateway 100.10.10.10. Red has BGP, and through BGP we see that there is a route to subnet 14.1.1.0, which is nothing but the subnet of red's network in the cloud. Now let's see what happens if I access the websites of blue and red. Now let's start with blue. So I have another VM here, which is nothing but a VM in the blue network, and I'm going to access blue's website from here. I open Internet Explorer. The address of the website is 14.1.1.10. As you can see, it brings up the website of blue. Now let's try this from red's network. So on red, I have a VM which is in red's network. I'm going to open Internet Explorer, and I'm going to access red's website. The IP address of that website is also 14.1.1.10. And as you can see, it takes us to the website of red. With this, we conclude the demo.
So as you could see, we could really isolate the traffic coming from the two on-premises networks, and though you have overlapping IPs in the cloud, it takes you to your respective IPs. So with that, I complete the virtualized network functions that we added in R2, and then now let's move on to Windows Server vNext. So let's start with a quick overview of what we have done in vNext. We have added a lot of key capabilities in vNext for the virtualized network functions. The first thing is that we have gone and completed the edge story in terms of the key functions that are required. We have gone and added a software load balancer, we have added a distributed firewall, and then we have gone and made a lot of good enhancements to the side-to-side gateway itself. We have created an extensible platform which allows you to bring your own virtualized network functions and insert them into your virtual network. Connectivity until R2 was possible only over side-to-side connections, but in vNext you can also come over high-speed connections like MPLS and Metro Ethernet, and we have ways to take the traffic from the MPLS router into your virtual network. The solution is flexible in the sense that there are a lot of scenarios where a tenant needs to go and access resources in the physical network. So we look at what those scenarios are, and we look at some solutions that we have come up with in vNext for that. All the services that we have added, the SLB, the enhancements to the gateway, firewall, etc., are highly available. They are all multi-tenant, so hence very cost effective. We have built Hyper-V to be the best host for hosting all these virtual network appliances running on any OS. A lot of good stuff has gone into management. The whole control and management of all these network functions is now done through the SDN network controller. The deployment is still handled by VMM. We have a much improved tenant self-service portal, which is very similar to the Azure WAP portal. It sits on top of the Azure networking stack. And then you can also bring your third-party tenant portals and build them on top of the network controller, SDN APIs, and PowerShell. So let's see how all these network functions integrate into the network controller. So the network controller has different planes. You have the management plane, which exposes REST APIs, and these REST APIs provide the capabilities to go and do tenant configuration and fabric configuration on all the network services. There is also a PowerShell layer that is sitting on top of the REST APIs for you to be able to do all these operations using PowerShell. It gives you a command line interface. And then we move on to the actual business intelligence, which is the control plane. And the business intelligence is where the actual configuration of all the network appliances happen. So we have a service module or a service manager for every single network function that we have built. So you have one for SLB, you have one for firewall, then you have a few for the gateway itself. And what these service modules do is they actually go and service the tenant and the fabric configuration requests. So for example, if you wanted to deploy a gateway, you have APIs for that, and those are executed by the service module here. If you are a tenant and you wanted to go and provision a site-to-site connection, the service manager or the service module will go and pick the gateway on which it has to place that particular connection, and it will go and provision the gateway. So all the intelligence is part of the network managers. And the way they do that is they go and directly configure the appliances underneath, and they use a variety of different interfaces. So we have OMI, we have WMI, WCF. It basically depends on the kind of interface that the virtual appliance has. Again, if you take the example of a gateway, all the configuration is done through WMI. So the network controller would make WMI calls to go and configure the gateway. Now, if you take the SLB and the firewall, we have agents in the Hyper-V host itself that need to be configured so that those network functions can work properly. And that configuration is also done by the network controller. So the entire management, configuration, etc., is managed by the network controller. Now let's delve into every individual virtualized function that we have added. Let's start with the virtualized edge gateway itself, and let's look at the enhancements that have been done there. The first and foremost is flexible multi-site connectivity with dynamic routing. So if you have deployed R2, you will know that if you have multiple connections coming from a single tenant to the gateway, you always had to terminate all of them on a single gateway on the cloud side. So you could not bring two very high capacity ones. So we have done away with that limitation in vNext. So now you could have multiple gateways, and you can terminate connections from the same tenant on two different gateways. So you can come up with high speed site-to-site connections there. And you can also route between them. So you could route from one on-prem to the other through the cloud, because now they are on different gateways. You can route between gateways. So we have provided all that flexibility. As I mentioned earlier, you not only can connect to your virtual networks over site-to-site, you can also connect to them over high-speed links. We will look at specific tunneling capabilities and encapsulations that we have added, which enable you to take the traffic into the virtual network. And there are a bunch of scenarios that we'll talk about where the VNet needs to go and access physical resources. We have added the capability in the gateway for that to make this possible. The redundancy that was there in R2 was 1:1, which needed a lot of VMs, and the whole the clustering solution had a lot of bugs. So we have done away with that, and we have brought in M+N redundancy, where you could have N standby gateways providing backup for M active gateways. So you need less number of VMs, and it's also a much more efficient solution, as we'll be looking at it. So in R2 we had support only for IQ2 based site-to-site IPsec tunnels. In vNext we are adding support for IQ1 based tunnels also, and we are also adding support for traffic selectors capability in IQ2. So these were two feedback items that came from a lot of our customers, and by providing these features, your interoperability between the cloud gateway and the gateway that is there on premises will improve, because a lot of organizations are connecting from Cisco or Juniper boxes. The throughput of the IQ2 tunnels has been increased to 1 gig. We had like 300 Mbps in R2, and you can do up to 1 gig in vNext. So let us delve deeper into BGP routing. So in BGP routing in vNext, we have gone and built a BGP route reflector, which basically goes and removes the control plane and separates it out. So what this means is that your gateways will now purely terminate site-to-site connections, and the routing etc. happens on a separate virtual machine. The advantage of this is that there is a single place which handles all the BGP pairings for all sites of a tenant and for all tenants. The other advantage is that if you are having to route traffic between gateways for the transit scenarios, you don't have to build peering meshes, since all these gateways are now peering with the route reflector, you don't have peering meshes anymore. So the gateway can also now be deployed to run just as a pure router. We support transit routing. So in this case, you could basically route traffic between the Contoso Washington and the Contoso Los Angeles sites through the gateway in the cloud. So that's a small animation that shows this. So if the link between the two sites goes down, you can now route the traffic through the cloud. We have built support for routing policies, which enable you to set policies which determine what kind of routes you want to advertise to your peers. If there is constant flapping of routes, we have a capability to go and dampen that so that your routing tables remain stable. And we have also added support for aggregation of routes. So you could take two similar /24 routes and aggregate them into a /16 route so that you have less number of advertisements going out. Next, we'll look at how the load balancing and high availability is possible through M+N. So in the M+N scheme of things, you have M active gateways and N standby gateways, and both these are configurable. So when you go and deploy this whole thing through VMM, you can say that here are my 10 VMs, I want 6 of them to be active and I want 4 of them to be standby. And you can later go and add and remove gateways. You can add more M gateways or N gateways, or you can remove, if you think that you have very high redundancy which you don't need, you can reduce the value of N, you can increase the value of M, we give you all the flexibility. And not only can you do this with a single pool, you can also go and deploy multiple pools. So you could have, say, 3 pools, each having a different M+N scheme. One could be doing 5+2, the other one could be doing 6+3, the third could be doing 7+4. And on each of these pools, you can run a set of gateway functions. You could do site to site on one, VPN on the other, etc. And the good part about this is that for all these pools, for this entire cluster of gateways, all that you need is a single public IP. Any connection request that comes in for the gateway gets assigned to the gateway at the time of provisioning, and I'll show you with an animation how all that works. So let's look at how the provisioning of a site-to-site connection works. So it starts with a request coming from the tenant portal where the tenant says that, hey, I want site-to-site, here is the capacity, right? And what the network controller does is the network controller knows what is the available capacity on all the M gateways. It picks the gateway that has the right capacity, and it goes and provisions the endpoint on that gateway, and it also goes and configures the required routing policies on the route reflector, which is the BGP router. In addition to that, it also goes and provisions a NAT. So since we are exposing a single public IP for this entire cluster of gateways, we have put the entire thing behind a NAT. So as part of the orchestration, the network controller also goes and configures a NAT. It basically says that any traffic or a connection request that is coming from this particular tenant, map it to gateway number 2, because that's the gateway that has been allotted for that connection. And once that happens, the actual site-to-site connection gets set up, and then BGP peering starts between the BGP router or gateway on premises and the route reflector in the cloud. And BGP goes and does all the route calculation, and once it has the entire set of routes, it sends all those routes to the network controller. And based on that, the network controller determines what the HNB policies are and provisions the policies on the virtual network. So after that, you can actually start routing traffic between on-premises and cloud. So this is how the provisioning of a site-to-site connection works. Let's see what happens when a gateway fails. So in this case, suppose gateway 2 fails. The network controller goes and picks another gateway. In this case, it's picked gateway 1, and it goes and provisions all the site-to-site connections that were there on gateway 2. It goes and provisions them on gateway 1. It also changes the NAT mapping. So the same IP now points to gateway 1, and as a result, the connection gets established to gateway 1. By the way, when you move the configuration, you still need to re-establish the connection, and because there is a right NAT mapping, the connection request goes to the right gateway. And once the connection is set up, your peering happens between the on-prem gateway and the router as usual. And because the gateway has changed, you need to go and update the HNB policies because the gateway for that particular subnet has changed. So all that is also handled. The BGP router just sends the updated routes to the network controller, which then plumbs the updated HNB policies down to the network. Now let's discuss a little about load balancing with SSTP VPN. Now most enterprises like to use SSL based solutions for VPN because they pass through firewalls, etc. So SSL based VPN is the most popular for remote access, and the Microsoft solution for an SSL based VPN is SSTP, as all of you know. So we have gone and built a solution that does load balancing for SSTP VPN. And the way that works is we have used, or rather we have gone and built a HTTPS proxy. Now anytime you go and establish an SSTP connection, the first thing that happens is you go and build a HTTPS connection to build the security, and then on top of that you build the SSTP tunnel, right? So what we are doing here is that first the address that you are connecting to has the identity of the tenant. So you have multiple tenants here. You have Woodgrove and Contoso. Both of them are connecting to the cloud. They want to go to their respective workloads. The only change that they have to do is in the address of the server, they have to append a tenant identity. And when the HTTPS request first goes out, it is terminated on the proxy. The proxy receives this tenant information through a GET request in the HTTP connection. So, and as part of provisioning the endpoint, which we saw in the previous slide, we saw how when a S2S connection request comes in, you go and pick the gateway, you provision the S2S endpoint on that, right? So just like that, even in the case of VPN, a gateway is picked, a VPN endpoint is provisioned on a gateway, and in addition to that, you go and provision the tenant to gateway mapping on the proxy. So the proxy now has a rule which says that if this tenant comes, go and send him to, in this case for Woodgrove, send him to gateway number 1, or for Contoso, send him to gateway number 2. So there is a rule like that provision. So the proxy knows which gateway to go to, and once it knows the gateway, it goes and sets up a HTTP connection to that gateway. So you have HTTPS between the user client and the proxy, and then HTTP connection between the proxy and the gateway, and you basically go and then establish the SSTP connection on top of this HTTPS HTTP path. You are not just limited to one proxy, you could also go and deploy a pool of proxies, and when you do that, you naturally put this whole setup behind a NAT so that you can use a single public IP to go and address this whole solution. And the failure of a gateway is kind of similar. In this case, let's assume that gateway number 1 fails. So the NAT, or rather the proxy has to be reconfigured. The network controller will go and allot, say, gateway number 2 for that connection, and then it will have to it goes and configures the proxy to say that for this particular tenant, instead of sending him to gateway number 1, send him to gateway 2. So all this additionally happens as part of the orchestration that we looked at earlier. So next, I would like to talk about specific cases, scenarios that we have enabled in Windows Server vNext for tenants to go and access resources in the physical network. So there are a bunch of use cases for that. The first is you could be coming into the cloud on a high speed network. So you have a lot of service providers that are now allowing, cloud service providers that are allowing tenants to connect to the cloud over an MPLS link. So you have a bunch of MPLS links coming in, all of them terminating on a router, right? So you want to take all the traffic from that router which is residing in the physical network or in the fabric network to the respective virtual networks. And then there's another use case where a tenant brings his, there are some workloads that he has on-prem, he brings it to the cloud and he has put them in the physical network. He has not taken them into the virtual network because they are not compatible with HNV. He has left them in the physical network and he wants to go and access them from his virtual network. So you have, in this case, you see both Contoso and Woodgrove have brought some kind of an appliance, they have put it in the cloud and they want to access it from their virtual networks. The third use case is that there could be a third-party appliance that is sitting in the physical network and providing different network services. Like the hoster could have gone and put a load balancer and he could say that, hey, I'm going to provide load balancing services to all my tenants. So these are 3 use cases where a virtual network needs to go and access something in the physical network. And we have come up with 2 solutions to make the connectivity possible, because in all these cases what you have to do is you have to bring the traffic from these appliances that are residing in the physical network, and they are typically VLAN isolated. So each of them, for every tenant, has a separate VLAN. We need to bring that traffic into the respective virtual networks. So the first solution is the multi-tenant L3 gateway. So the L3 gateway is basically programmed to take VLANs and then map them to the virtual network at the back. So we could have, you could have rules which say VLAN number 40 goes to tenant 1, VLAN number 50 goes to tenant 2. So anytime traffic comes on VLAN number 40, it will take that traffic and it will put it in the compartment or in the HNB network of tenant 1, and then it will do that for all the other tenants. What you have to additionally do when you go and deploy an L3 gateway solution is that you have to provision those VLANs along the path on all the network appliances between the gateway and the physical appliance. And then it's multi-tenant, so you could have rules like this built for multiple tenants. There is routing possible with this also. You could either go and configure static routes to route traffic between your physical network and your virtual network, or you could also use BGP. And this gateway also supports M+N redundancy for high availability and load balancing. It is also integrated with SCVMM network controller, just like the site-to-site gateway. The other solution that we have makes use of GRE tunnels. So one disadvantage with the previous solution, the L3 gateway solution, is that you have VLANs in your physical network and then you have the gateway, and then there are a lot of network appliances in between. And to use the L3 gateway, you have to go and actually create that VLAN on all the network appliances on the path. And this is a cumbersome task for a lot of hosters. So we have a different solution for people who don't like to do that, and that is GRE. What we essentially do there is we build a GRE tunnel between the physical appliance and the gateway, and we tunnel all the tenant traffic into the gateway. And the gateway again is multi-tenant. It is capable of looking at different GRE tunnels and mapping the traffic on the GRE tunnel to the virtual network. It is also possible to put traffic of multiple tenants on a single GRE tunnel, and when you do that, you can use the key field in the header of the GRE packet to differentiate or discriminate between tenants. So you could have a single GRE tunnel. Each tenant comes with a different key value, and the gateway looks at the key value. It knows that key value 1 is for so and so tenant, and it sends the traffic into the right virtual network. Both the solutions, that is the L3 gateway solution and the GRE solution, work only for L3 traffic. We cannot tunnel or we cannot map L2 traffic directly into the virtual network today. The GRE solution itself is interoperable with various different physical appliances. Like in the case of MPLS, it interoperates well with a typical Cisco router that terminates MPLS, or a Juniper router. If it is a load balancer providing network services in the physical network, we also interoperate through GRE with that. The management of all this is again through SCVMM and network controller. The throughput of the GRE tunnel is higher than site to site. You can do up to 2.5 gig for the entire gateway for all the tenants put together, and you can even do 2.5 gig per tunnel. So you could have a single tenant using up all the 2.5 gig also. And by the way, this solution is not only available in VNext, we have also backported it to 2012R2. Now let us see GRE in action. So let me describe what the setup is. So here we have two resources, one for green and one for blue, and these resources are residing in the physical network. And then we have green and blue having their virtual networks in the cloud, and the cloud workloads want to naturally access these resources. We have a router in between which basically routes traffic between the physical network and the virtual network, and that is possible because both these resources talk to the router on different VLANs. Green uses 4020, blue uses 4000, and the router basically maps all this traffic to two different GRE tunnels, 4020 for green and 4000 for blue, and when these two tunnels hit the gateway maps the traffic into the virtual network. So let's see how this works in the demo.
I'll first show you the blue and the green resources in the fabric network. This is the blue resource with IP address 10.1.100 using VLAN 4000. This is the green resource having the same IP address but using VLAN 4020. Next, we will look at the configuration of the Cisco router. On the Cisco router, I have configured two VRFs, one for tenant blue and another for tenant green. I have also configured two GRE tunnels, one for VRF blue that uses key 4000 and another for VRF green that uses key 4020. I have also configured two VLANs on this router, one for VRF blue that uses VLAN 4000 and one for VRF green that uses VLAN 4020. Next, we will look at the configuration on the cloud side. We'll start with VMM. I have created two VM networks for this demo, the blue GRE VM network and the green GRE VM network. Going into the blue GRE VM network, connectivity is over a GRE tunnel. VMM now provides you the capability to add GRE tunnels in addition to IPsec tunnels. If you look at this GRE tunnel, you will see that the remote endpoint is a Cisco router and the key being used is 4000. This is the green VM network for GRE. Green also has a GRE tunnel terminating on the same router but using key 4020. Next, we will look at the configuration on the cloud gateway itself. On the cloud gateway, we have two GRE interfaces. The first one uses key 4020 and is assigned to green, and the second one uses key 4000 and is assigned to blue. Next, we move to the cloud workloads. I have a VM here for blue that resides in blue's VNet and a VM for green that resides in green's VNet. From the blue VM, I am going to access the blue resource. The address is 10.1.100 and it brings up the blue website. From the green VM, I am going to access green's resource. The IP address is the same, but this time it brings up the green website. With this, we conclude the demo.
So that is, traffic isolation for you when it's going back and forth between a virtual network and a physical resource using GRE. So I have another demo. So by the way, this previous demo that we just saw was on 2012 R2. So you can go and use this capability right away in 2012 R2. I have another demo, and this time with Windows Server vNext. And here I have an interesting setup. So basically I am talking about an organization called Orange that has two sites, site 1 and site 2. And they both have high speed tunnels or high capacity site tunnels that are coming into the cloud, because there is a VNet for Orange in the cloud that is hosting a web server. Now, because these are high speed, high capacity connections, we cannot put them both on the same gateway. So I have created a gateway pool in the cloud, and these tunnels go and terminate on different gateways. I have also put a NAT right in front so that you can address the connection, both these connections, to the IP address or the public IP address of the NAT. And one more thing that's happening here is that I'll also show you the route reflector. In this case, the route reflector is actually going and residing on gateway number 2. So you have in Windows Server vNext, you will have different options. You can either go and have a separate virtual machine that hosts your route reflector, or if you already have a pool of 10 gateways, you could put the route reflector on one of them. You can even have multiple route reflectors. You could have like 4 route reflectors on 4 different gateways. So there's a lot of flexibility that we provide there. So in this case, the route reflector will be on gateway 2. So I'll show you all this when we look at the demo. Now the deployment of the gateway pool, the configuration of the gateway endpoints, etc. is all done by the network controller. And we currently have scripts that we have written on top of the REST interface, which goes and applies the REST JSON objects for the gateway, for BGP, etc. So let's look at the demo.
We'll start with the enterprise end. I'm on site 1 and this is gateway 1. The IP address of the gateway is 31.1.1.1. It has a side-to-side connection going to 100.10.10.100, which is the IP address of the NAT. It has BGP enabled and it is peering with the address 10.1.1.4, which is the IP address of the route reflector running in the cloud. Now let's go to site 2. I'm on gateway 2. This gateway has an IP address 31.1.2.1. It has a VPN side-to-side connection going to 100.10.10.100, which is again the NAT. It has BGP enabled and it is peering with 10.1.1.4, which is the same route reflector in the cloud. Now let us look at the configuration on the cloud. I have two gateways in the cloud. I'm on Cloud Gateway 1. Cloud Gateway 1 has one side-to-side connection, and the destination of this connection is 31121, and this is also the IP address of site 2. We have BGP enabled on this gateway, but it is not functioning as a route reflector. Now let us look at Cloud Gateway 2. Cloud Gateway 2 also has a VPN side-to-side connection, and the destination of this connection is 31111, which is the IP address of site 1. So essentially, site 1 is terminating on Cloud Gateway 2 and site 2 is terminating on Cloud Gateway 1. Now Cloud Gateway 2 also has BGP enabled, and it is configured to be the route reflector. Now I'm going to access the website of Orange in the cloud from the two on-premises sites. Let us start with site 1. Orange VM1 is a VM in site 1. The IP address of the website is 10224, and that brings up the web page of Orange in the cloud. Next, I'm going to move to site 2. Orange VM2 is a VM in site 2, and I'm going to access the same website from here. That brings up the website of Orange in the cloud. With this, we conclude the demo.
So in this demo, in the allocation of sites to gateways was all done by the network controller. You saw that site 1 was going to gateway 2, site 2 goes to gateway 1. All that is assigned by the network controller. And the monitoring solutions that we build will be able to tell you where exactly your connections are. If you are a hoster, you want to know who are the tenants connecting, how many connections are coming in, which connection is on which gateway, because the whole thing has now been automated, right? So the monitoring solution will tell you where exactly things are going. So next we move to software load balancer, firewall, service insertion, and my colleague Greg will talk about it.
All right, thanks, Anand. Still here. All right. So how many of you have actually created a cloud service in Azure to load balance one of your apps? A few of you? Well, I encourage the rest of you to do so, because that is basically the same software load balancer that we're bringing to Windows Server, and we're going to make available to all of you to put into your own clouds. The exact same technology. So let's talk about what it actually consists of and how it'll apply to your deployments. So the software load balancer, it basically consists of, the entry point is what we call SLB MUX. The SLB MUX is what contains your virtual IP. You can have many of these, anywhere from 1 up to whatever your scale is. And these are what receive the traffic that comes in, and then they direct it out to all of the backends that are behind it, the DIPs, the pool of machines that make up the pool behind the VIP. Now, these are highly available. They're aware of SDN, so they're talking to our network controller. They're able to send traffic into specific virtual networks, so each VIP can belong to a virtual network and an application of that virtual network. So they're also multi-tenant in that regard as well, because you can have many virtual networks behind these MUXes. They're highly available, as I said. They do the high availability through BGP, also very similar to the way the gateways do their high availability. They advertise up routes for the VIPs. They're basically /32 routes, so that the routers know how to talk back down and know which MUX to send the traffic to. And of course, these are deployed and managed through SCVMM. I'll talk about that in a little more detail. Oh, and there goes some happy packets flowing through the network, getting load balanced away. All right, so the load balancer is made up of the MUX and the network controller, are kind of the two starting points that you need. You program against the network controller, and that then configures the MUX. It also goes and talks to the host agent and programs the host agents to know, how to remove the encapsulation when the traffic arrives at the VMs. Host agents live on the Hyper-V host, of course, where your tenant VMs are located. And so the MUX, basically its purpose is it has the VIPs, as I said, and it spreads the traffic to the back ends. We also have an SLB manager that runs in the controller. This is basically what receives all the APIs, defines the APIs that you program against, or that the Azure Stack will use to call into the controller to program the SLB. So as far as how do you get this up and running, well, you're going to start out with the controller. You'll have that up, and you'll have that available. This is actually the same controller that Azure uses as well, the same SLB manager module that runs in the controller that Azure uses. We've ported that over to Windows Server. And so you're going to start by deploying, through SCVMM, the SLB MUX instances. Each one of these is essentially its own VM that you can deploy across your environment. They can even exist in different racks in different subnets. And then you also deploy onto your host to get them up and running with the host agent. This is what, again, receives the communication from the controller in order to add and remove the virtualization policy. So as soon as that MUX comes up, VMM will also configure it to peer with the physical switches. So as soon as it starts peering, the controller can then start to create VIPs on it. Those VIPs will then get advertised up to each of the switches up above. And in fact, all of the MUXes will advertise all of the VIPs up so that the switches themselves can use ECMP to basically send the traffic to any of the MUXes that are available. I'll show that in a little more detail in a minute when we talk about high availability. So then once you have it up and running, you use the Azure Stack. Again, the same Azure UI today that you would use to create a cloud service. That same UI will go and program the controller. It'll create the VIPs. It'll let you map the pool members behind the VIP. It'll go program the VIP in the MUX, and then it'll push out the policy to the host agent so that it knows what to do as well. Now let's actually step through, step by step, as traffic comes in from your edge routing infrastructure and works its way into a VIP. So it's going to come in from your router, from some external point, some client machine or app, and it's going to go make a request to a particular VIP. Your routers will know how to route to that because SLB MUX advertised up that, hey, this VIP is located here, and so they know how to route down to it. SLB MUX is then going to look at that packet, and it's going to decide the destination based on basically 2, 3, or 5 tuple hashing. So it's going to hash based on the source and destination IP, the source and destination ports, and the source and the TCP protocol. No source and destination there. So it's going to basically decide which of the backends to send it to based on that. It's then going to encapsulate it onto the correct virtual network using VXLAN or NVGRE, and it's then going to send it to whichever one of the tenant VMs it picked within that network. When it gets there, the host agent will remove the encapsulation, give the packet to the tenant VM, so now the tenant VM can go and calculate its response. So now let's look at the return path. Now the return path is actually a little bit different because the return does not go through the MUX. So the tenant will generate its response. It'll send it back into the virtual switch where the host agent will get that response. The host agent then will detect, oh, this is actually a response to a VIP. And it's just going to send it straight back out to the routing infrastructure. It's not going to go back through the MUX. So in that regard, it reduces the load on your MUX, sends the traffic straight out, and you go straight to its destination. It does this by rewriting the source IP so that to the destination it looks like it came from the VIP, but it didn't actually come from the VIP. It actually came directly from the load-balanced VM. Next, I'm going to show you how high availability works. I mentioned that every instance of the MUX advertises up to the switching infrastructure that it has the VIPs available. So there's a route coming down for all the /32s of the VIPs. So now the switches can use ECMP and basically pick. It'll pin, basically, when it does its hash, the switches do their hashing, they'll generally pin to one of the MUXes. But each MUX can handle any request and can send the traffic to any tenant on any of the virtual networks that are behind it. Now, of course, if one of the MUXes goes down, and the response, though, before we get there, the response, again, for all cases, goes through DSR back out to the routing infrastructure, bypassing the MUX. Get my clicks to go. All right, so now one of the muxes is going to fail. Since this is a BGP peer, through BGP, the switches detect that this mux is no longer available, and now they know they only have one path available, and so all requests now will come in through the active mux. Now, of course, if you have more than two, they would get spread across the two that are still, or more than two that are still available. But the traffic will then go through that one mux and get redirected out to all the tenant VMs. Return path is still unchanged. It goes directly out. Basically goes the same way as it normally would. So let's quickly jump into an environment that I have here that I actually have this configured. Not the failover, just the SLB. So let me switch over. I'm on number 8. All right, what you see here is a window where I'm actually basically doing some REST API calls to the network controller. I'm doing all of this programming through REST and JSON. This is the raw programming interface to the controller. Now, when all of you can try it out, the real UI that we'll use, which will be the Azure stack, you can do it today through Azure. But in the future, you'll have that available to use here as well, assuming you don't want to use JSON. What I've already done here is I've created a virtual network that has an application deployed. This is a basic blog application, 2-tier app with 2 different subnets. One for the front end, one for the back end. I've actually got a diagram here to show you. I've got my front end. I've got my back end, which is actually on a different subnet. I don't show it here, but it's on a different subnet. And I'm going to create a VIP out in front on the 50.0.0.0.2 network that would represent the public internet. I've got a client machine that represents a public client that's going in and accessing that VIP. The traffic, the program I'm going to do through REST into the network controller. The controller will then, you'll see a whole bunch of output as the controller then goes and spits all this policy out to the host that contain these VMs and the SLB mux so that it can actually do the load balancing. You can see my virtual network is working. I've got just a script here that's running. This is on one of the front-end VMs. It's address 168.0.21. I'm pinging to the back end, which is .1.21. And you can see that it's working. So let me just connect to my blog. It's my fake networking blog. I can connect to each of the 4 backends. Now, I've gone ahead and set one of the fourth one up as just the default IIS page so that you can actually see as we do the load balancing that it actually is rotating between the backends. So every once in a while, you'll see this page come up instead. So I'm going to query using OVSDB tool, OVSDB client. This is actually the same OVSDB client that you may use for doing to a switch that opens the VTEP schema. We ported that to Windows and have that available now to query against the host. And I'm going to go and push in a JSON document through REST into the network controller. It basically has the load balancer VIP defined, the IP address that I want at the front end. And then it has each of the back-end DIPs. Each of those 4 machines that I showed you are defined as well to say how to map that VIP into the DIP at the back end. This is actually going to run for probably a few seconds here. While it's running, I'll also show you, oh, actually that was faster than I expected, 24 seconds. We'll just scroll back real quick, and if we go through here, we'll see in the JSON the 4 network interfaces. Here are the back-end IPs. Each one of these represents one of the network interfaces of one of the VMs. And if I scroll up a little farther, we'll see the VIP that represents the private IP. Here's the front-end IP configuration, and here's the VIP that I'm programming to basically say for my front end. At this point, I can also query OVSDB. You can see that these are now marked as load balanced. And we should be able to now go to our client machine. And with a little bit of luck, well, we got the IIS machine right off the bat. Let's just keep hitting it again. We might have to get it to refresh the cache. There we go. We actually got the real one this time. Oh, there it goes. So you can see it is actually rotating through all of them at the back end, and it is doing load balancing. All right, switch back. Number 5, I believe. Number 5. All right. So that was software load balancing. Let's talk a little bit about the data center firewall. So how many of you have used port ACLs with Hyper-V or know that we have extended port ACLs with Hyper-V in 2012 R2? Okay, a few of you. Well, these are basically the same concept with a few additions. So they're made basically primarily 5-tuple rules for restricting traffic for east-west communication between the VMs. You can do it based on subnet. You can do it based on IP address. So you can summarize. And basically, you can restrict, for example, in my example, which I'll show you in a minute, you can restrict the traffic from the front-end VMs from being able to talk to each other by saying, deny all traffic on the same subnet that I'm on, for example. But still allow traffic to the other subnet in my virtual network. One of the key differences, though, now is that it's now integrated into our network controller, so that you don't have to go like you do today and program against every Hyper-V host to set the ACLs. You can actually go to the network controller as a single place. If you're doing it programmatically, you would do it through JSON and REST. Of course, you'll be able to do it also through the Azure Stack as well, in the same way that Azure will let you do firewall rules today. There are a few other additions. We will also have security groups as well, so you'll be able to group your rules, so you don't have to do it on a machine-by-machine basis. You could say, apply this rule to everybody in this subnet. So instead of, like I say, applying it to every individual machine like you have to do today with ACLs, you can go say everything in the subnet. Then even if you create a new machine, add it to that subnet, it'll get the rules applied automatically. One of the other key differences also is now we're blocking by default. So when you create a VM, we'll actually block until you go in and create a rule to let traffic through. So in that way, it's actually much more secure. It's very easy to create that single rule that says let everything through. Oh, so before we get to service chaining, let me actually go back to this demo environment. We'll actually apply a firewall rule. So we're back in the demo environment. So if I open up my this machine here, this is one of my front-end tier machines. So this is one of my IS web servers. And you notice I did the queries here earlier where I actually connected to the other 4 or the other 3 of my front ends. I'm going to close these so that we can do fresh queries again. And what I'm going to do is I'm going to apply an ACL that basically says block all traffic that originates on the same subnet. Basically what this is going to do is this is going to do the equivalent of a PV-LAN, basically saying that if you're on the same subnet as me, I can't talk to you and you can't talk to me. So in that way, we're restricting if one web server gets compromised, you can't attack the other ones. So let's go apply that rule. There we go. So there it goes. These are pretty simple rules. If I scroll back, you can see here's one of the rules. So deny from any source if the destination is on my same subnet. And we have one, I believe, for the other direction as well, inbound and outbound. So now let's go back to this machine, and if everything went according to plan, only one of these should actually respond. The rest will just sit there and spin. So one responded. This one did not. This one did not. Oh, actually, I did them all on the same machine. Okay, those are just going to sit there and spin. Oh, actually, one went through. This might be the... Nope, that one didn't go through either. Did he go through? Nope. Nope. Okay. So the only one that went through was the one on my local machine here. Of course, it went through on the local machine because it never actually went out on the network. So you can see the ACLs got applied. We basically just modified that same JSON document, pushed it into REST. Now that policy got applied from the controller and went out to every VM that's on your network. Okay. So that's the firewall. Service chaining, this is the last concept I'm going to talk about. And this is also something that's completely new in the next version of Windows Server. So service chaining is the idea that you have a lot of, and this is really kind of one of the keys behind virtual network function, is that you have a lot of these physical appliances from different vendors on your on-premises data centers. And you want to go to the cloud, and you want to bring those capabilities of those third-party appliances into the cloud with you, whether it's your own cloud, your own private cloud. You want those same functions to work in those virtual networks. If you're going to a hoster, you want to bring your appliance into that hoster. And you then want to be able to control the traffic that goes to your VMs so that you can block the bad traffic from getting to the good VM. So every once in a while, you'll see a red packet here representing the evil packet that you don't want to get there. So what we want you to be able to do is bring in an appliance into your virtual network and redirect traffic to that appliance based on whatever rules you define, similar rules to what you would define for the firewall. You'll be able to bring in these appliances from vendors that have already built appliances that run on Hyper-V. So they have Linux appliances, BSD appliances, even Windows appliances, if you can find one. They are all out there, and we want them to be able to come in and run on top of Windows and work in this environment. We don't want those vendors to have to change their appliances either. They can be pretty much agnostic to the fact that there's this service chaining. They'll just get the packets like they would if they were on a VLAN. And we want to apply the same types of groups as well. So you apply the rules to a subnet, and then anything that's connected to the subnet will get those rules applied to them. So let's actually walk through how it works real quick. I'm going to just build out this whole slide real quick. And basically the way you do it is you define a rule that's like a 5-tuple firewall rule. That's what you see in the bottom left. Let's see if I can point with this. Oh, I guess no pointing on that. A rule that's like a 5-tuple firewall rule. So in this case, I'm saying if my destination is anywhere in this subnet, then send it to this service chain. In this case, the service chain contains a third-party antivirus VM. So we basically tell it to redirect all traffic that's going to this subnet to this appliance. And then, of course, you say which of the virtual networks you want to apply to, because this potentially rule and service chain could apply to many different virtual networks. Push that into the controller. The controller will then figure out where are all the machines that, that this rule could apply to that are on this virtual network, and it goes and pushes that policy out to those Hyper-V hosts. And as soon as that policy gets there, then the traffic, anytime it enters this subnet, whether it's from the gateway or from VMs on that network, the appliance will, the traffic will get redirected to that appliance. Now it does this by, as the traffic comes in and it matches one of these rules, basically rewriting the packet so that its destination is now the antivirus VM. It'll encapsulate it using VXLAN or NVGRE, send it to its destination host where the VM is running, where it'll unencapsulate it. It'll then pass that packet on to the VM unencapsulated. So that VM doesn't need the appliance VM doesn't need to know anything about the service chaining. It just knows I'm getting a packet for destination 02. I can go and do whatever inspection I want, deep inspection, whatever it wants to do, it can do to it. You can manage that appliance using whatever management tools that vendor gives you. You know, and they can span potentially even across to your on-premises appliances of the same vendor. And then when it's finished, that appliance can make a decision if it's going to forward it on or block it, drop the packet. It'll forward it back out onto the network, unencapsulated. Hyper-V will then know that this is a packet that's actually going to my VM this time for real. And so it will re-encapsulate it with NVGRE or VXLAN and send it on to its destination VM, where it'll arrive, unencapsulated, then the VM can process it. So that's service chaining. Now, of course, we know that a lot of these appliances are Linux-based. We know that there are also some that are BSD-based. So we're doing a lot of work. We have a team that works on just the Linux integration components in the Linux kernel to build very high-performance Linux drivers that run in Linux and BSD. And so we've been doing a lot of work over the past year, and we're continuing to do this work, pushing these updates into the Linux kernel so that we can get performance out of these Linux VMs that is as good as Windows on Hyper-V, and that is as good as these Linux VMs can run on another competitor's platform as well. So it's an ongoing effort. As you know, things get faster, we have to continue to make more improvements. But you know, if you've been following this over time, these have been improving, and it's an ongoing effort. So with that, we've talked about all the virtual network functions that we have available. So there's places you can get more info. And I have to run to another session in about 5 minutes, but Anand will be here if I run out of time to answer more questions. So thank you. Go ahead. Yeah, there is a heartbeat. The exact mechanism, I believe it's just basically like I don't think it's a direct ping, but I think it just does basic requests. And if it detects that one went down, then it will... You're
talking about the failure of the VM sitting
the VM itself, the dips, yeah.
Oh, okay.
Yeah. There is a way to define them. I don't know the details of what those are, but you can define health monitor. Yeah, it's exactly the same as what you do in Azure. So if you know what you do in Azure or look that up, it would be the same. It's basically a probe that you define.
Yeah.
Yes?
So right now with gateways, you have to have a dedicated Hyper-V host to the gateway. Are we going to be able to run gateways as well as load balancers as well as other network roles on those same hosts? Or are you going to need to have separate hosts for separate networks?
So we don't have a conscious restriction to do that. But then that would not be recommended because each of these are network functions. They need they need the CPU, they are performing critical tasks. So it's recommended to separate out some of that. But if you want, you can run it. There is technically nothing stopping that from being configured that way. Yes, so we are supporting VXLAN network virtualization. So you could have a gateway or SLB, taking traffic on one side coming from the internet or the physical network, and then at the back your network virtualization could be doing VXLAN.
Yeah. So why support BGP when the slowest approach is times living protocol? Do you support OSPF in between a load balancer in 21?
No, so all the the advertisement that Greg spoke about to advertise the VIPs and all that happens through BGP. That is the only protocol we support.
It has the slowest convergence time of almost every routing protocol.
Okay, the reason why we chose BGP again is because Azure uses BGP. That's number one, and number two is that from our studies and talking to customers, we found that a lot of the data centers actually run BGP. So it was natural to take a dependency on a protocol for this purpose, which is being deployed. Yeah. Can you come closer? Sorry, I'm not able to hear you.
Yeah, or go to the microphone. So
Yeah. Okay.
BGP EVPN.
Yeah.
The distribution of the routes use the VXLAN route. The IP routes using the VXLAN entity across the BGP.
So you're asking if we support that?
Yeah, VNext.
No, I don't think
So you're saying that to peer with a switch over VXLAN?
Exactly.
I don't know. We do not support that.
Are there going to be any restrictions to using this with the Gov Cloud, the Azure Gov Cloud? Or is it
So
going to be
this is
exactly the
for
same?
Windows Server deployments. So it's your own private deployments that you're using. So Azure has its own implementation. I don't know what their details are with the Gov Cloud in particular, and how they expose it there.
Right. Okay, thank you.
Any other questions? All right, thanks.
Thank you.